So, how's everyone? I'm thinking we should slowly start because, yes, it's 5 past 5 already, and other people will maybe join, but it will take us a few minutes to go through the beginning slides, and they won't miss much. Shall we?
Sure.
Okay. We're I'm going to talk in English. I hope everyone's comfortable with it, mainly because some of our attendees are not Romanian, and even though I think everyone here is Romanian for now, they might join later. But if there's anything you don't understand, we can explain it. Just go ahead and interrupt me. I don't mind. We will also use the Google Meet chat here. If you have some kind of questions and you think maybe we should address them later during the talk, you can write them there, and before the end we'll go through everything in the chat and try to answer everything. This is going to be, I encourage it to be an open discussion. So, yes, let's go.
All right. You might hear every now and then a ping when someone is joining, so I hope that's not too disturbing or annoying. So, good afternoon and a warm welcome to all of you. Thank you for deciding to spend your afternoon today together with us. We will be spending together the next hour or so going through functional thinking concepts, of course, guided by my colleague Mihai. As a general approach, as Mihai mentioned, we would kindly ask you to keep your microphones on mute just so that we can reduce the background noise as much as possible. But if you feel at any point that you would like to address a question, please feel free to do so. Otherwise, as Mihai mentioned, you can write it in the chat and we'll make sure we go through them and answer them at the end of the session. So before we start diving into the topic today, I would just like to take a minute to introduce you to crafting software innovation. So we are a group of 40 people. We are talented and highly passionate, and we look at software development and product development as a craft overall. We are based in the heart of Transylvania, in Cluj-Napoca. Cluj is a very big technology hub and university hub. And it's probably the most popular city in Romania, like we like to call it. Of course, we have our capital, Bucharest, but we believe that Cluj is the sole capital of Romania overall. So, for crafting, what we do and what we do best is that we specialize in web and mobile development and as well as product development. But we have a very special place in our heart for functional programming languages, especially Elixir and Erlang. So without further ado, I would like to allow Mihai, our speaker today. He's an architect in crafting software. He has more than 14 years of experience, more than 22 technologies, and I think more than 10 projects already at crafting software, at least.
I think this mainly means I'm old.
This means you're precious.
As the numbers go up, I'm getting older, so it's not a good relation between these two things. But anyhow, thank you. Anka, for the nice introduction. Okay, did you want to add anything else, or should we dive right into it?
I think we're good to go. Hello, Robert. Hello, Rado. It's great to have you.
Okay, so we've gone through the introduction slides. Let's go into the subject of this meetup. It's nice to see everyone here. We're going to talk about functional thinking and what does, and yes, we'll elaborate in a few minutes. So what to expect from this talk? A reiteration of functional programming concept and tools, explanations on why they are helpful, examples in various programming languages, not just Elixir, even though this was organized on the Elixir meetup group. We'll talk about general functional programming concepts with many languages examples. We'll just scratch the surface. We're not going to dive too deep in anything. Of course, we can dive a bit deeper than the surface here and there together if you want to. Feel free to raise any questions and to debate any examples that I've prepared for you. I'm by no means, I don't claim I'm an expert in anything, so I might be wrong. Also, some of the examples are in languages that are out of my comfort zone, and those might have some mistakes in there too, but hopefully not. So, also, I don't have a good explanation about the event avatar that you got in the email notifications. This was raised to me by a couple of persons. There's a lady in there. We have no idea how she got there and how to remove her, but let's just enjoy life and move forward. In the end, we're going to offer 2 tickets to the Taxylvania conference. And we'll see how to how you can get those. I'm going to display a question for you guys, and the first 2 people who answer it in the Meet chat, the one where we greeted each other before, we'll get the tickets. So yeah, feel free to be comfortable with that, locate it, and make sure you know how to type an answer in there. Also, to identify yourselves and to claim your tickets, please afterwards use the contact@craftingsoftware email address. And also you can use it for anything else. If you want to reach us, you can do so on the Meetup platform or by email or visit our website or anything. All right, so this is what you can expect from this meeting. Let's go. Even if not on purpose, you might have thought about your programs in a functional matter if you used functions like map, filter, reduce, and the other ones in the family. If you ever passed a function as a parameter to another function, or returned the function, or used a value instead of a variable, that means using let or val in different languages, or const instead of let or var, which declares something mutable. We'll go deeper into these topics in a few. Or wrote a pure function, one that doesn't have side effects. So even if not on purpose, even if this is not your comfort zone, you might have done things in a functional manner, and that's great. And we'll see why in a few. I'd like to begin by sharing a quote that I like a lot, and I like it because it reflects on my experience. So, learning Haskell is much like learning to program for the first time. It's fun and it forces you to think differently. This is a quote from Learn New Haskell for Great Good, book that I like a lot, and I like it. I like this quote because you can, in my opinion, you can relate functional. You can replace Haskell with functional programming. That was my experience, and I think it's true for many of us. Learning to use functional programming is much like learning to program for the first time. It's very fun. So the functional programming concepts that we'll cover and discuss a bit are declarative code, the discipline of immutability, concurrency in the context of functional versus imperative program, higher order functions, and pure functions versus side effects. Our first concept is declarative code versus imperative code. So when writing code in a declarative manner, you should worry about what and let the compiler and the runtime worry about the how. Declarative code is more explicit, it should be more obvious, and side effects are isolated in declarative code. Also, exceptions are avoided. Let's see an example. So you give the a comparative example actually. So in imperative code, you give the computer a set of instructions, and the computer does what you want in a sequence. So a practical example, a rule in your app or program says a new password must be at least 9 characters long. So there's a list of new passwords and we want to validate them. In JavaScript, using imperative program, you would use a for, you would iterate the list, and you will create an empty list first, then loop as many times as there are elements in your original list, do your checks, and mutate. If one element passes the checks, then you push it in your empty list declared at the beginning. This the same as the compiler. In this example, we can reason about how this program executes. And that's not very natural. This is simple at this level, but as the complexity, this is a trivial example, of course, and as the complexity grows, it gets harder and harder. And let's see how we would do the same with declarative code. So declarative code is a process of constantly defining what instead of how. It's more readable. It tells what we want to achieve. We don't care much about the how. We shouldn't. We should be able to reason at a theoretical level about our goal. And of course, the result is the same. So in declarative code, the exact same task as before can be solved by having a function that validates our rule and just filter. We're not telling in our program how to do it, how to loop, how to keep a list of whatever matches and so on and so forth. So we just tell to filter and how to filter. And this is more readable, I'd argue. Of course, I cheated a bit in here because to make things even more meaningful, I extracted the rule in a function with a meaningful name. I can do the same here and make it a bit more readable, but still, this is how it looks in a declarative way versus an imperative way. Next, immutability. So another quote from the same book on Haskell. If you say that A is 5, you can't say it's something else later because you just said it was 5. What are you, some kind of a liar? So use values as much as possible instead of variables, as they don't change. And once a thing is created, it's that thing forever. Create a new thing instead of changing it. In pure functional programming languages, there are no variables. Everything is a value. How we would declare such values, we can enforce it by the tools of the language that we're using, or I'd argue that almost all modern programming languages have this. I've given here examples in JavaScript, Kotlin, and of course Elixir. My personal rule is if I write some code, a piece of code, and I need a mutable variable, I need to take a step back and rethink it a bit. We can also see the previous example and look at the immutability of things because it shows it quite well. In the imperative example, we mutated a lot. So there was the index iterator that we used in the for loop that changes at every step. There was the list of long passwords that we needed to collect that was mutated at every time the rule passed. And in the declarative code, things were not mutated. So we just had an initial list of passwords, which we transformed using a rule and a function, and we obtained a new list. As I've said, modern languages usually have built-in support for this. We can do it in Kotlin as well, even with classes. So if you have, you can do it in a mutable way, in which you have a class structure, which is a car, and you initialize it with name, and at a later time you change that name. This is not mutable. This is not immutable. Let's make it immutable. Kotlin offers support for that as well. Instead of, as I've mentioned before, instead of using a var, you can use a val for the name property of the car, and that never changes then. Once it's created, it will have the same name forever. You have to create a new instance of this class to obtain a new name. We'll dive into a more involved example and see more benefits of this way of writing your programs in a bit. So why is immutability important? It avoids side effects. If it can change, you don't have to worry about its state, about the state of your program at all times, or a state of a variable. It makes code more predictable, reliable, easier to reason about, and multi-threaded programs are safer. We'll see an example of how this happens right here. So this is a connection to our next concept, which is concurrency in of a program that is written in a functional matter with immutability, and one that's imperative and things change. As you can see here, we have an instance of a car class, the one we talked about before as well. And there are two threads that consume this resource. The first thread gets the name of the car. It says that it gets the value BMW. And the second thread mutates it at a later time, changes the car name, for example. After that point, the first thread assumes that the car name is what it got before, and that's wrong because it changed. And this is classic race condition example, a read, modify, write. What are the object-oriented program solution for this, and imperative programming solutions are locks and mutexes. This is using locks, and I've done this a lot of years before getting into functional programming, and I'd argue it's not easy to do so, and it often leads to deadlocks, which are hard to investigate and find and fix. So let's see the same example with an immutable class in Kotlin. The same car, which has its property name immutable because it's declared with the val keyword. Other than that, the same types, the same data structure. Let's see what happens. So there's this resource car. The first thread gets the car name. The second thread wants a car with a different name. It cannot mutate the existing one, so it will create a new one and get a new copy of it with the name it needs. This causes no problem for thread 1. And thread 1 can move forward correctly, assuming that the car name is BMW. So thread T1 can compute without worrying, since the other thread has another copy. No locks are necessary in this example, and immutability assures that the shared data is thread safe. So more abstract, things that should not be modified cannot be modified. If this is enforced at the language level and by the way you write your programs, then your programs can be safer and easier to reason about and to debug and so on. Of course, these kind of trivial examples and theory cannot be achieved 100% in the real world. Modifiable shared state must exist in a real world app. So, and how do we approach it in functional programming? We approach it by using the state in isolation and pushing the side effects at the edges of our system. For example, the database, the file system, the user interface, and so on. And we keep the core and all the business logic as functional as possible, using immutability and such. And in this way, we can achieve a safer and a more readable, maintainable application. So what about the web front ends? Can they be functional, immutable, and pure? I'd argue that yes, they can be, but most of the times they are not. And to explain, we can achieve it in web front ends because each update can be a transformation based on the input and render a new version of your HTML that is passed to the compiling engine. Practical, concrete examples are React, that renders, for example, a new output based on probes and state changes via the render function, or by pure functional components. You can also achieve this with other technologies, even with HTML and custom elements out of the box that also are also built in with a similar principle in which there is a render function, and that render function just outputs new HTML based on the input that changes or attributes and props and so on. I'd argue that this can be pretty much functional at the concept level. There are other technologies out there that can do this, for example, lit HTML, Vue, and so on. Also, there are functional programming languages especially built for the front end, like Elm, which is very nice and lifts all these concepts to the front end. And back to our questions, most of the time front end code is not functional because there may be JavaScript functions at a low level. Of course, there are tons of libraries and frameworks and tools built on top of that, but at the low level, it's the same thing. It's JavaScript functions that change the state of existing elements to render new states. Of course, immutability has a downside. There's no free cake anywhere, not even with functional programming and immutability, because many immutable objects may fill up the memory, overload the garbage collector, but there are solutions for this by using specialized data structures that provide immutability and are also optimized for creating new copies and sharing memory for the common parts. These are the persistent data structures. I'm just mentioning them. We won't go too deep into them, but the concept there is that a persistent data structure always preserves the previous version of itself, and they are immutable. Operations don't update the structure, but yield a new version. There are different libraries and frameworks out there for different languages. There's one for Android programming. For JavaScript, there's Immutable.js, developed by Facebook, if I'm not wrong. And yes, for Elixir and other functional programming languages, these data structures are built in. I have I prepared a small example in Java here. where we're using an immutable data structure, and at each step there's a new list generated and the original list is not affected. The next concept we're going to talk about is functions. Functions in the context of functional programming, of course. So, pure functions. A function is pure by definition if it depends only on the input and it has no side effects. It's a transformation of data rather than a mutation of data and state. And this is closer to the mathematical definition of a function. So let's see an example of what I just said. There's impure function that adds to a given input parameter value read from a file. So this one depends, of course it's a trivial example, but you can meet this a lot in real life programs. For example, you have some input data and you have some data that lies somewhere in the database, and you need to mix and match those two, and your function gets the input provided to it and then reads some stuff from the database or from the file system, like in this example, and then it gives you the result. This is not pure because it depends on the state of the world outside of the function. So a pure function should always get all its input via parameters, and it should not depend on anything else. Pure functions, if they are called with the same parameters twice or a million times, you can rely on them to provide the same results. And this is called referential transparency. And it also allows the compiler to reason about the program's behavior, and it allows you to prove a function is correct. It achieves the desired results with, of course, automated tests, unit integration, whatever. Always 100% of the times, in my experience, it's easier to write tests for functions that are pure, that for logic that is written in a functional matter, because you don't need mocks, stubs, dependency injection, and so on. So of course, all these tools exist out there, and they are very useful, and we should know about them and use them when needed. But I'd argue that they bring complexity to our programs and tests as well. And that's what we're trying to achieve. Keep the complexity level as low as possible so that technical debt doesn't accumulate, and that we can reason about our programs and that we can maintain them. And last idea here is that of course you need very complex functions here and there, but you can achieve those by using multiple simpler functions and gluing them together, and also keep a principle of purity in your functions. Yes, testing, it's what I just talked about. So in functional programming with pure functions, it's easier to test fewer mocks or none and stubs. And the same about dependency injection. In functional programming, functions are first-class citizens. And what does this mean? A function is just a value and it's not treated any different from any other data. In most programming languages, function and data are regarded as different things, but in functional programming languages, they are the same. For example, in F#, which I've used on a few projects before, the way you declare a function and the way you declare a value, which is just a piece of data, syntax-wise, they are not different at all. They are the same. And I liked that a lot about F#, and I kept this practice when going to other languages like JavaScript and TypeScript, where the syntax allows you either to use the function keyword to declare a function, or you can just use the lambda syntax and use a const to declare your function. And in this way, also in JavaScript and TypeScript, functions and other data are more the same than different. Functions can also take other functions as parameters or create and return new functions as their results. And this concept and this type of functions are called higher order functions. You've surely used them before, and the most common examples here are map, filter, and reduce, which are maybe present everywhere, which take a function as a parameter to work it on every element of the collection they are applied on. Let's talk a bit about side effects in relation with the pure functions we just talked about. So in our previous example with impure functions, our function also grabbed some data as input from the file system. Side effect is when a function or a piece of code touches and modifies the state outside its parameters and result. So for example, here a simple add function, which besides adding, writes the result to a file. This is modifying the state of the outside world, and this type of functions will need mocks and dependency injections for testing. So of course, this example here is pretty trivial, but we can think of something more complex that we might see in our everyday code, in which a function that does a computation writes the result to a database, for example. And when trying to test this, you have a problem because you need to mock out the database. Write a mock for it or use dependency injection to have a mock in there, or other. There are tools. Of course, there are lots of tools out there, but if I'd argue that you can simplify all this by avoiding side effects as much as possible. So the example here would be that this function should not write the result to the file system, even though that might be a requirement of our feature that we're implementing. And we can achieve the same result by isolating the computation in a pure function, and then at a later time writing that result somewhere where we need it. So recap: side effects mutate variables scoped outside of the function. Other examples are that of side effects are writing to a file in the file system, writing to a database, deleting something from somewhere, sending data through the network, sending data to the user interface, modifying the user interface actually. So can we get rid of all this? Should our programs not use, since we're saying that side effects are bad, should our programs not use databases, file systems, network screens? Of course not. Of course we need this to make our apps meaningful, but instead what we can do is isolate these side effects, pushing them, as I said before, at the edges of our system, so that the rest of our code remains pure, easy to reason about, to test, to maintain, to fix, so on and so forth. Other advantages of pure functions are that they can be called in any order. They can be executed on any CPU core. Concurrency is not a problem here. And compilers in advanced pure functional languages like Haskell can tell by formally analyzing your code whether it's concurrent or not. It can stop you from shooting yourself in the foot with deadlocks, race conditions, and the like. Higher order functions, on the same topic of functions, as I've mentioned, and as you probably already know, are functions that can take other functions as parameters and return other functions as results. And let's see an example. So we want a piece of code that compresses files using zip or RAR format. And let's see how we do this in traditional Java. It's the strategy pattern, in which we have a general strategy interface and then several different implementations of that, which have overrides for the compress method and use a different technique to compress the files, whether it's zip or RAR. And then there's a function that decides the strategy based on some input, and it returns a different implementation of the compression strategy based on the strategy input. So this is a lot of code and a lot of ceremony for achieving something that it's not so complex and that we can achieve in a much simpler way using higher order functions. The same example as before in TypeScript uses gets the same input of the files that need to be compressed, and just a function that can actually does the compression using different technique as before. And if we want to use zip technology or method, we pass that function as a parameter to the compress function, and the same for the RAR strategy. I'm not saying that Java doesn't have modern Java doesn't have the tooling to achieve this in a similar and simpler way. I'm sure it does, but this is just an example of older object-oriented thinking that actually needed a lot of ceremony to achieve goals that can be achieved way simpler using higher order functions. It was a lot of pain at a certain point with different versions of Java in which you had to do this, and you knew. I'm speaking from personal experience here, in which I knew there are simpler tools out there, but for production constraints, which we all have, we had to use a certain language and a certain version of it. And these are all the tools you had in your toolbox, and you had to do this. And it wasn't nice knowing that there are simpler ways to do it out there. So this sums up our touching of the higher order functions subject and of functions a bit in general, and we'll get to our next topic, which is currying. Also related to functions, of course. In functional programming, everything is related to functions. And yes, let's see about this concept. It takes its name from Haskell Curry, mathematician with important influence on functional programming. It has both a concept and the language name. He has both a language and a concept named after him. And what does currying actually mean? It's partial function application, and it means that a function in mathematics, a function can have only one parameter. So a function with multiple parameters is rewritten as a series of new functions, each one with only one parameter, and they are composed together. We'll see an example in a bit. Yes, there's another definition that I've taken from somewhere in here. But let's see the example, which might make things clear. So there's a function that multiplies three numbers, actually. And this is its type definition and its definition. And let's see if we need to obtain a function that multiplies two numbers with 9, with the number 9. We can achieve this by partially applying the multiply three numbers function with just one argument. So we've passed only one parameter. This is a partial functional application. This is what currying is about. And then we have a new function which can take two parameters, which are actually the other two from the beginning. And we can go forward with this and obtain a function that multiplies with 18. And what it does to get defined, it applies the previous function with just one parameter. So we have, using partial application, we have defined different utility functions, let's say. This can also be achieved in JavaScript, and we'll also see where it's useful. So we've talked about the how, and we'll see its advantages in a bit as well. Of course, in JavaScript, being not a functional programming language, some tasks like currying and partial application are not easy to achieve, and you have to use different tricks and different syntax options to obtain a similar effect, but still it's possible. So a classical definition of a sum function is this, and this of course cannot be partially applied. It's not curried, but you can write curried version of the same function, which is by declaring that sum curried is a function that takes a number and returns a function that takes a number that returns the sum of the two. And to apply these, of course, the first one, it's applied in well-known way, but the second one, if you want to apply it completely, let's say not partially, you'd have to use this syntax and obtain the same result. But what actually happens here is that you apply the function to one parameter, the first one, and then after this computation is done, you obtain a function that expects another parameter, which is the second one we mentioned here, and you get the same result. Okay, where is this useful? So for example, you want to iterate on a list and not actually iterate, but add one to each element. How would you do that if you don't have the curried version available? Well, you'd have to do it like this. You map over the numbers list, and you have a lambda expression here, a function that takes each element of the list and sums it with 1. But if if you have your curried version available, you can do this simpler, maybe not very easy to read for someone that is not a big fan of functional programming, but I'd argue that it makes the whole thing much more simpler at a theoretical level. And how you can achieve this with the curried version is that, okay, what's the parameter that the map function expects? Well, it's a function that takes one parameter of the type of the elements in the list. And this is exactly what we have with the partial application of the sum curried function. And we can take this even further with a higher level function that it's called apply add n to each, and it takes number, it takes list, and then it does the map the same as before. And then when you want to call this, you call it very simple like this. Of course, this is a bit forced example in JavaScript. It's not the idiomatic way to do things here, but I was just arguing that it is possible, and if you and your team, of course, are a fan of this kind of approach, you can do it. But you should value more readability of your code, and if this kind of tasks are not easy to comprehend by everyone in your team, then you should stick to the classic version, which makes your code readable and understandable for everyone, because that is of much more value than having short and smart versions in here. As I've said before about F#, things here are built this way naturally. So in this kind of language, it feels natural to use currying and partial application in opposition a bit with JavaScript, let's say. The same example here in F# is a bit easier to understand and read, of course, by F# programmers. And let's see how Elixir handles the subject of currying and partial application. So in Elixir, functions can have the same name with different arities. That refers to different overrides, let's say, in other languages. And creating a Haskell style compile time notational currying is not possible because of this language choice. But for forward piping operations, we can partially apply functions in Elixir as well, but this refers to the first argument of the function only. So the first argument is field is the same as the last one in other functional programming languages. We'll see an example in a bit to make things more clear. So the map function, which doubles every element in a list in this example, would be applied like this, but you can also use the forward pipe operator and just pass the list, push it forward through the pipe to the map function that is written here only with the second argument. So in Elixir, the first parameter is injected for partial application, versus F#, which does things differently, and other languages from the same area, from the same family here, for example, of Camel, but Haskell as well. This is done, is built differently actually, because the map function by definition takes the list parameter last, and in a forward piping syntax, you know that the result of the previous computation, in which in our case this is actually the input parameter, is applied last to the function map. So in this case, the last parameter is injected. And yes, let's talk a bit about chaining and pipes, if we've already seen them in examples here. So the pipe forward operator passes the result on the left side of the function to the right side. So the result of what happens here is passed to the next computation. It's actually the same concept. Of course, in both examples here, we've just talked about the subtle differences in how the compiler does this. where is this useful, the forward pipe operator? For example, if you need to change several applications and instead of getting into this brackets hell, you can separate and make things more clear actually, by using the forward pipe operator. And I'd argue that this version using the forward pipe is is closer to how we reason about it. And by this I mean that here the first function that executes is the one from the inside, and then it goes to the outside and more outside and so on. And this is in reverse order of how we read it actually, because when you first look at the code, see, oh, okay, there's the foo function, which gets the input from this, but wait, this needs this to execute so that it gets in its input and so on. But on the forward pipe, it's actually written the same as you think it. So, okay, this executes, and what do we do with the result? We push it forward to this, and then to this, and then to this. So it's the natural order of things. And this is another example as well with a real with existing functions from the Elixir language. In F#, we have the same options. We've talked about F# and this in a previous example, so we'll not explain it too much. And what about JavaScript and TypeScript? So, of course, in JavaScript, there is no forward pipe operator yet. There were some language proposals. We'll see what we'll have in the future, but there are tricks and different libraries that can achieve a similar effect and result. We can use, for example, Lodash here, and Lodash has some built-in functions that always return a result that can be pushed forward to the next function that is applied. And I'd argue that we can achieve a similar effect here. But of course, you don't have to use Lodash. Every function, from example, from the array object, every function that returns an array can be chained with the next one that does the same. You can chain as many map filter function as you'd like. You can even throw in there some reduce or find, but you have to fix the types and make sure that the type that is returned by one can be taken by the next one. The pipe backward operator also exists in some languages, but it's not very much used. I know that F# has it. I'm not sure if others have it. I'm not sure I ever used it, but it's good to know that it exists. I think the last concept we're going to talk about today is pattern matching and destructuring, and maybe a bit about recursivity in a minute. What is pattern matching? It is a mechanism for checking a value against a pattern. A successful match can also deconstruct a value into its constituent parts, and we can also say that it's a more powerful version of the switch statement from imperative programming. Some examples. This is how it's done in Kotlin. So we have a person that has the name and age properties in Elixir as well. We can destructure to values A, B, and C. The tuple structure here in F#, it's it needs a bit more syntax. It's actually not just destructuring, but it's pattern matching with different cases for matching. So you can match list and see if it's empty, you get this result. If it's has 42, then you get this result. You can also use wildcards and just get one element if your list is has 3 elements and you're interested in the one in the middle. If it has more elements, you can go through a more general branch, case branch that destructures the list into its head and tail, and then you can apply the same function recursively on the tail and until you find the result that you're looking for. In F#, recursive functions need to be flagged that they are recursive by the rec keyword. There's an example in Scala as well. So here we have an abstract class notification and some case classes, email, SMS, and voice recording, each one with its properties. And we can pattern match a notification object against each our case classes and also extract the relevant information. Like email has sender, title, and body, but in our pattern matching, we're only interested in sender and title, and we can use a wildcard for the last. So this one's a powerful concept as well, pattern matching and destructuring. It exists in a lot of modern languages, but its syntax might be very different. It's there in JavaScript, and a bit of curiosity here. As far as I know, it doesn't exist in languages like C# and Java, but there's the try-catch constructs, which I'd argue are very similar to pattern matching because you can have different catch branches which match against the type and also get the value from it if the type is matched. Discriminated unions. A discriminated union is a pattern that indicates to the compiler all the possible types that the newly created type can represent, also known as algebraic data types. So this exists in F#, exists in Java, also exists in TypeScript. A simple example is the type shape, which is actually a union of rectangle or circle or prism, and with each one with its properties. In Java, we have the optional type. We have something similar in Elixir, which is a tagged tuple. The type animal with which can be either cat with some properties and so on. Our last topic today, and I'm going to wrap it up maybe in 5 minutes, so that it gives you an idea on where we are in this talk. So in functional programming languages, in pure ones, actually, you don't have any loops for, while, whatever. But if the built-in functions on collections, the ones we talked about, map, reduce, filter, everything else, if they don't satisfy you, your other tool here is recursion. And I'm sure we all met it at some point in high school or early years of programming, and haven't used it a lot since then. But there are cases when you need to use this, and you need to know about what possible issues it can bring, like Stack Overflow. But there are patterns that can save you from this, which is the accumulator and continuation pattern. Also, it needs the tail call optimization. In JavaScript ES6, it exists. So what do I mean by Stack Overflow? Is that when you use a recursive function and it needs to call itself for a very large number of for a lot of a very large number of times it needs to call itself. Each call to itself goes to the stack frame, and if this number grows very large, you get the infamous Stack Overflow exception. You can guard yourself from this with the patterns I told you about, and let me show you an example. So we want to build the filter function. Let's see how we can do this in JavaScript. We get a list of numbers, which is the input, a list of axes, and the function that validates that an element passes the filter or not. We, if the list is empty, then the result is empty, of course. If not, we destructure it to its head and tail. We validate if the head matches the filter function. If it does, we return it. If it wrapped in a list. If it doesn't, we don't. And we do the same for the tail, and then we concatenate the two by spreading and joining in the new list. And this function is recursive. It calls itself for the tail, and this happens again and again until the tail is empty, and then it goes back and concatenates everything. So this is a recursive function which for very large lists can cause the Stack Overflow exception that we talked about. But we have an option to avoid that, and this is just a pattern, it's nothing different. And let's see how we would write this filter function in a tail recursive manner. The same as before, the function takes a list of axes as parameters, function that validates each one, and this time an accumulator as well. And what we do here is the same. Do a check. If the list is empty, return what we've accumulated so far. If it's not, we destructure it to its head and tail, and then we try to find the new accumulator, which is the current accumulated values together with the head, if the head matches the filter function, if not, just the values accumulated so far in the accumulator. And once we compute this, we can go on and call the function again. There's a syntax error here. It should have said tail recursive filter. So call the function again, and this pattern can prevent the Stack Overflow exception if the language has tail call optimization built in, meaning that the last instruction of the function, of the recursive function, is calling itself, and it doesn't have to keep anything else in the frame, in the stack frame, and the compiler then knows how to optimize this to prevent Stack Overflow. The difference between the one before is that here the filter was not the last instruction, and the compiler had to, actually the runtime, at runtime in the stack frame, we need to hold the reference to the continuation, because after the function is called itself recursively, then it still needs to take the result and do a computation with it. And this was the last topic in our talk. I have a big list of my sources for preparing this, and good sources that I'd recommend for further learning. I'll share this with you on the meetup page. And before we get to the $1 million Pennsylvania tickets question, let's take a moment to discuss some of your questions so far. Does anyone have some questions? I see that not at the moment. Well, I can take them afterwards as well. If you want to get in touch with me, please do so, and we can talk about anything that you might want related to this presentation, of course. All right. And now for the question we prepared. So as Anka mentioned in the introduction, or I did, I don't remember, we have a couple of Pennsylvania tickets to offer. And to get them, what you have to do is answer the next question and write the answer in the Meet chat, the Google Meet chat that we have in here, and the first two who answer will get the ticket. So the question is, what is the result of the following Elixir computation? I'll leave it on screen for a few minutes. I'll get a glass of water in the meantime. I'll I'll explain the question a bit. So there's a string with these values. The first operation we apply is to split it into single characters. Then we filter out the ones that are digits. So we'll just keep the digits. And then we'll change the digits to integers. And then each one, if we'll map on each number that we have. If it's odd, we'll double it, and then we'll join back to a string. And I have a hint as well. The answer to this question is the same as the answer to what is the meaning of life, the universe, and everything. Okay, we have an answer. And two answers, yay! Thank you very much. Well, this was all on my part, and it seems that the hour is later than we wanted it to be. We wanted to keep things shorter, and yeah, thank you very much. This is it on my side. Thank you for being here and for listening to me. I really hope this was helpful to you. As I said in the beginning, I didn't want to dive too deep. Maybe I have in some situations. But yeah, let's hope that it helped you. Thank you.